Hello and welcome to our webinar on sustainability. I have prepared a very interesting agenda for you all. We're gonna start first about a short introduction to Fiberline. We're gonna talk about the raw materials used in the composite industry. We're gonna talk about the conversion processes and the cons and pros of the conversion processes and the energy involved in the different conversion processes. Afterwards, we're going to take a short overview of a comparison or the energy demand of producing different building materials. We're going to have a short introduction to the ways of recycling composites, and I'm going to give you a short overview of how we as a Fiberline view the future of composite materials. There will be a few minutes for questions if any of you will have some. Let's jump straight into it. Many of you know us, but we are a family-run, medium-sized company. We are about 100 plus employees with the sales and product development offices in Denmark and the production currently now in Poland. We were founded back in '79 by Henrik and Dorte Thorning, and we supply construction profiles for the building industry. Our core business is the manufacturing and process manufacturing of composite profiles by the process called pultrusion. We do also a lot of assembly and machining of pultruded composite profiles as well. Let's have a short overview of the raw materials used in composites. And we're going to talk about fiber reinforced composites, but because the word composites may also apply, for instance, to reinforced concrete, which is also a sort of composite material. Let's first have a look at the fibers. The fibers are actually the load carrying part and the most important part of a fiber reinforced composite material. For the fibers, there are a lot of different fibers to choose from, but the most used fibers in the composite industry are glass fibers, aramid fibers, also very lately carbon fibers as well. You have also basalt fibers and something very new and upcoming are natural fibers, but more on them later on. The fibers can also have different lengths. They can be short fibers from a few millimeters to a few centimeters, intermediate fibers, long fibers, and what we use in the pultrusion process called continuous fibers. So fibers or endless fibers, so very, very long fibers. The resins are liquids in our processes or in the process of composites, and there are two to choose from, and more or less. You have a thermoset resins and thermoplastic resins. More on the differences also later, but the most common thermoset resins are epoxy, polyester, and vinyl ester resins. Polyurethane is also used in different production methods. For the thermoplastic, polypropylene on PVC, and the main difference is that the thermoplastic resins can be molten down and reused time after time, where the thermoset resins form very strong bonds which can actually not be molded down. Next to the fibers and resins, what also goes into the profiles are price reducing additives and performance increasing additives. And here we are talking about color pigmentations, release agents, fillers, fire retardants, and so on. You see actually on the right, we see an image of a pultruded profile where you can see the glass fibers and fabrics, but you can also see how the soft fibers with addition with the resin turn into a solid profile. But let's have a look on how the glass fibers are produced and the energy demand for producing glass fibers, and let's also have a look of how polyester resins are manufactured. So the main material for producing glass fibers is actually sand or silica. But other ingredients are added to the process to primarily reduce the working temperature or the melting temperature of glass. The glass normally will melt with the temperatures above 1400 degrees Celsius, but by adding aluminum oxide and kalium oxide or limestone, can actually bring the melting temperature of glass down, and you can also enhance the mechanical properties of glass. The furnace is fired by gas to reach these higher temperatures, and it's normally controlled in 3 stages. So you have to cool down the molten sand, which has now reached a liquid state. The fiber formation is achieved by extruding the molten sand through bushings made of platinum. You can imagine the friction and the temperature in those furnaces, and then afterwards it's spooled on bobbins in different sizes. The last step after the fibers have been spooled on our bobbins is actually applying chemical sizing to the glass. This is a separate process, a chemical process, which gives the glass a much rougher surface, so it can adhere better to the resins in the later processes. In general, energy consumption for melting glass down is about 30 gigajoule per ton. And what this number means in comparison to other fibers, I'm going to come later to that on a later slide. But this is fairly energy heavy process, and the most furnaces today on most glass manufacturers are producing glass by burning natural gas. Unsaturated polyester. This is more chemical process. It's actually the idea here is that you mix the ingredients in huge tanks, and the polyester is actually formed by a reaction of dibasic organic acids, malic anhydride, which is normally produced by processing butane, and butane is a liquid petroleum, or is based on a petroleum, on raw crude oil. And this organic acid is actually mixed in huge barrels with controlling the temperature with the glycols, which are sugar alcohols, and afterwards it's dissolved in a typical styrene monomer to form unsaturated polyester. The mixing itself actually does not require a lot of energy, and the cooling and heating processes are also fairly low in temperature. But the general energy consumption is low for the processing. But when you look at the calorific value, this is high because you have carbonized organic acid, so you have also used the butane. So you are looking at the energy of 100 to 120 gigajoules per ton. So a lot more energy in the resins than in the fiberglass production. Those numbers are very important because the normal split in the composite industry between resins and fibers are normally dependent on the process you use. For the pultrusion, normally we use 75 to 80% of glass, and the remaining is resin. So let's have a look at the different conversion processes we have for composite manufacturing. The most common process which you can actually use by yourself in your own garage or home shop is actually hand layup. And in this process, you will normally lay fibers down in a die and layer by layer, and then afterwards applying some sort of resins. Normally epoxy and polyester resins are used here. This is very labor intense process, and it's normally not used any longer for industrial applications. For huge parts, here we're primarily talking of wind turbine blades or boats and huge three-dimensional shapes. Resin transfer molding is used, where you still have to hand lay the different fabrics and fibers down in a huge glaive or die. Afterwards, you will bag it in and suck the air out of your mold, and afterwards turn on the pump to add resin to the mold. Afterwards, depending on the size of the molds, they will cure by room temperature, or you can also have a temperature increase to increase the cure time and turnover time. This is also energy heavy process. A hand layup will normally cure at room temperature. Filament winding is used primarily to manufacture round tubes, square tubes as well. And this process is very similar to pultrusion process, but here by filament winding you are limited by the length of your mandrel, of rotating mandrel. The benefits by all of these processes is that you can use more or less any fibers and any resins, but you cannot manufacture all geometries on the different processes. Pultrusion process is really well known for its consistency and the high output per line or per hour needed. And the pultrusion process looks like this in its very simple formation. On the left side, we have the raw material, dry raw materials with primarily fiberglass or different fiber types. And the resin injection is actually performed by injecting the resin directly into the heating and curing die. The only energy we need for this process are the heaters needed for this, and the heaters for normal polyester resin will run in a temperature range of 80 to 150 degrees. For other resin and glass fiber and fiber systems, you may have to increase or decrease the temperature. But the process is fairly energy efficient since we actually only have to heat the die to a very, very low temperature to start the reaction and to have the reaction of polymerization continuing. We use electric or hydraulic pulling devices to pull the reinforcement through the die and out of the machine. Afterwards, we cut the profiles to length. So when we compare the energy input in our process to other manufacturing methods, we are very low on energy. So if we take a look at the square tube 60 by 60 and the carbon footprint and energy demand for manufacturing this profile, we are looking at about 160 megajoule of manufacturing 1 meter of this square tube. And this was calculated by using EUCS eco calculator, where the manufacturers of the raw materials have provided the raw data for different resin systems, resin types, additives, and the data for fiber materials are also provided. What we as a manufacturer can affect here, or what we can input is our energy and where our energy is coming from. Being manufacturer in Denmark, we have about 40% of our energy is coming from renewable sources, so we can put this in and have our carbon footprint, for instance, decreased. Down here is a pie chart where you can see that at about 18% of the energy that is used to produce this square tube, which weighs around 2 kilos a meter, is actually coming from the conversion process or the pultrusion. The rest of the carbon footprint and energy demand is coming from the raw materials that are going into producing this square tube. So now you're probably asking yourself, how does this compare to other more traditional materials that are used in the building industry? Yeah, let's have a look at this. And this is actually based by a paper by Richard A. Daniel from 2010, where he had a look at the comparison of 5 different bridges for the Dutch province of Zeeland in the southwest part of Holland. You can see it on the left on the map. Here, the municipality wants to have a look at the energy demand and the impact of water pollution and air pollution of the different building materials that were available. The criteria was to make 2 bridges or 2 spans of 13 meter with a width of 1.6 meter and on a service load of 400 kilogram per square meter. The loading dock had a free span of 13 meters, and on the second span has to be mounted on a pontoon which can flow up and down with the tides of the river. So he had a look at the bridges made from structural steel, with one span weighing around 3,000 kilograms. The second option was stainless steel. In this case, it was a IZ 316, and the third option or pick was a composite bridge, which had a weight of 2,000 kilos. This also includes all the brackets and steel parts. The fourth option was an aluminum bridge, which was the lightest in this case, and the third option was a concrete bridge, which was actually not possible due to the pontoon and the extreme heavy weight. And what he actually found out was that the bridge made for composites was actually needed much less energy in manufacturing and also polluted the air and water during the production and installation at the lifetime at least. We have access to this paper, so if anyone of you will need a good reading, we can forward this afterwards. But what he found out was that the structural steel, depending of it, if it comes from virgin material or it's recycled, requires about 46 to 36 megajoule per kilogram to manufacture. Stainless steel was obviously due to the nature due to more chemical or stuff. It needed more energy, which is 6954, and glass fiber normally primarily comes from virgin material. It's about 33 megajoule per kilogram. Those numbers can be compared to the previous slides where I mentioned 140 megajoule per kilogram, but this composites back in the days was made without fire retardant agents, so this is why the number is so lower. Aluminium was the most energy demanded material to make, also in the recycling process. Reinforced concrete fairly low, but this was later neglected due to the heavy weight of the structure. Yeah, as seen, the load or pollution of air can be seen on the upper diagram on the right side, and the pollution of water can be seen on the lower diagram. As mentioned, this paper is very comprehensive on all of this, and it explains how the calculation were made and where the data is deriving from, so we can have full traceability of how this calculation is made. So back in the days, the municipality of Zealand, they decided to go with the composite bridge due to the lower impact on the environment, and this is how the bridge actually turned out to be. Next slide is a bit more about recycling and how the ways that are to recycle composite materials today. I have listed 5 methods here that are really very well known out there and that are used in higher or lower degree. First one is mechanical grinding, and what you actually here do is you grind the composites, and you can afterwards separate the FRP rich powder from the matrix rich powder. And the separate, and when you have done this, the powders can be used as additives in processes, in other processes afterwards, like molding processes. By using this method, you clearly destroy all the properties of fibers and all the properties of matrices, and you in the end you end up with the powder that can be used to decrease values of resins of fibers in later processing. Pyrolysis is a thermal process where you, with high temperature, can burn away the resins, and you can extract the fibers. By using this process, you actually damage the fibers to a certain degree that they cannot be used as structural part as if they were virgin fibers. This process also requires a lot of energy as an input, and it's also questionable what to do with the fibers which are so damaged and where the mechanical properties of the fibers are unknown. Solvolysis is a similar process, but instead of using energy, you use chemical treatment or solvents, normally water and alcohol or acid mixed, to extract the resins and fibers. This process requires a lot of chemical treatment, and it is also limited to a smaller parts, smaller pieces, because you need to submerge all the materials into huge tanks. Fairly new process, high voltage pulse fragmentation, this is an electromechanical process where you with high voltage pulses break down the bonds of in the resins in the matrices, and you can extract the fibers. And by using this process, the fibers are the fibers that come out as recycled have decent properties and can actually be reused later on in other processes. But all those 4 processes mentioned before are highly or cost a lot, and the fibers in the end costing more than virgin fibers. But the last process we're going to talk regarding recycling, and this is the one we use at Fiberline, is cement co-processing. And this is a process developed about 15 years ago, where we use the scrap material as raw material in the cement production. So what we do when we have when we produce a bit scrap in our production, or when we receive some profiles back that need to be recycled, we send those huge profiles, which normally can easily be over 12 meter long. We send it to a grinding mill in the north part of Hamburg in Germany. The large profiles are being grinded to smaller pieces, about 2 to 5 centimeter. You see actually some of them, or you see image of them on the left picture. Afterwards, after grinding, the profiles are being filled in big bags and shipped to different cement manufacturing plants. And the raw materials in our profiles are very well known. As mentioned, we have about 75% glass fibers, which are primarily made from sand or silica, and the rest is resin with a very high calorific value, so energy. The sand is used as a raw material in cement production, and the polyester is burned away as a fuel source. And by doing this, the cement manufacturers can save huge amount of coal, but also limited their use of sand and limestone. So if the cement manufacturers recycled or reused 1,000 tons of composite waste, they can save about 150 tons of aluminum oxide, about 200 tons of sand, 200 tons of limestone, and about 450 tons of coal. When burned in the huge rotating ovens, all the materials melt, and the sand also, or the glass also melts to sand, and in the end you end up with very fine powder, which is then used in cement and afterwards in the process of making concrete. This process is can only be used or is primarily used by bolt shooters, because we know exactly what is in the profiles. This is very hard to use on the large wind turbine blades, because they have a lot of other materials than glass and resins. They have also a huge amount of balsa woods. They have carbon fibers. They have wiring and lighting conductors as well, which is actually not good when you manufacture cement. You need to know what is in the ovens, what is rotating over there. So a lot of the huge wind turbine blades, and the next slide really hurts me when I show you. They are put in huge landfills because currently recycling them or reusing them is not an economically viable process. Next slide, a bit about future of composite materials and how we at Fiberline think about heading in the future with our process and the composite materials. So what we know today is much more than we knew back 20 years ago when we started developing the construction profiles for the building industry. We have much better understanding of the materials and the behavior of the materials. A lot of research has gone into optimizing the cross section and to the materials that we use in the processes. So we can optimize the cross sections using less materials, for instance, in the webs, where we know that we know much more about the buckling and the folding issues of thin wall cross sections, thereby using less materials to achieve greater load capacities. So the easiest way, but still keeping the same resins and fibers, is actually just to have a look at the cross section and optimize them with the knowledge that we have currently. But also the next step could be to have a look at the fibers. As we saw in the previous slides, the fibers contribute to the strength and stiffness, but but glass fibers, due to having to mold down sand each time, requires a lot of energy. Many manufacturers have started to look at other energy sources than natural gas. Some manufacturers in the United States have tried to use electricity, but due to that electricity spikes are also, or the electricity is also sometimes very high. This is not always the cheapest method of making fiberglass. But other fiber options are out there, and I have gathered here a few of the most common natural fibers, where the sea soil and the flax and hemp fibers have been actually tried out in the process of pultrusion and other processes of manufacturing composites. If we try to take a look on how much energy is required to manufacture one ton of sea soil, flax, and hemp fibers compared to glass fibers, this is how the equation looks like. So manufacturing natural fibers is about 1/10 of the energy of manufacturing glass fibers, and about 1/100 of the energy of manufacturing carbon fibers. There are obviously some issues of using natural fibers, and the first one is that our knowledge of natural fibers in the structural industry is very limited, and the second one is also the moisture issue. But to combat this, I found actually when researching for this PowerPoint presentation of sustainability, I found a paper where a patent in the United States was granted to a company or to patent seekers on making pultruded sandwich elements with the core material being natural fibers, and the skin layer would be more traditional fibers. This will solve a lot of the issues of water migration, but also give you a very strong and stiff outer surface, and the profiles actually being optimized by weight and strength relations as well. This could be one of the options for the pultruders to work with more natural fibers in the future. The second one is the resins. So there are three steps to have a look at the resins. First of all, the easiest one is to adding a non-recyclable polyethylene PET waste to the thermosetting resins. This is already being done and tested by several of the larger resin manufacturers. And this is actually very simple. Taking the PET bottles, the colored PET bottle, which cannot be recycled in the same way, and using this as an additive to thermoset resins. This can be easily achieved or made and also implemented in the running productions that we already have. The second one is using thermoplastic resins. The beneficial part of using thermoplastic resins is that they can be easily recycled and reused, because just by increasing the temperature slightly, they can be molded down, and you can have a pure resin again, and the fibers will be unharmed. But there are a few issues with thermoplastic resins, primarily the strength capacity as well, but also the research in making structural parts of thermoplastic resins is also not that researched as using thermosetting resins. The next one, and the one that has a very bright future, is using bio-based resins, and those resins can be extracted from a lot of different materials. But research is also primarily looking at wood dust, algae, and vegetable oils. By using enhanced chemical processes, manufacturers can easily make usable resins from bio-based sources as well. So this was about 30 minutes, and this was my presentation. So if you have any questions, I'll try to answer them. And just a few information: the same webinar will be held in the German language on the 27th of October on week 39. So if you
there's a few questions here. The first one is I think you've actually just explained that, because Dr. Weiss is writing, warum nicht in Deutsch?
Yeah, Dr. Weiss, the same webinar will be held in the German language on the 27th of October. So if you want to, you can today subscribe to this one, and this one will be held by my colleague Christian Scholze.
Okay, and then there's another one here. Now, I don't know if you understand it. I don't. Someone has just written Andre Palo. That makes any sense to you? No? That is the question, Andre Palo.
I think that's a name, probably a name.
Yeah, but okay, moving on to the next one. Someone here writes, natural fibers, nice idea, but this material are victim of biodeterioration by fungi, as for example wood. The main advantages of GFK is its durability. We use the beams for bridges.
Yeah, I totally agree, but we have to look at the overall cost as well, and when we see that natural fibers are starting to get at a price level where we can easily actually swap them in. And I also agree that there is some issues on durability, but it could be that a combination of natural fibers and the more traditional fibers could be a way to go to bridge the gap of having strong and durable profiles, but also having composite profiles that have low energy or environmental impact.
Okay, great. Moving on to the next one. What are your thoughts about disassembling constructions made from GRP? Will this be a way to go in the future?
Yeah, a good question. Obviously, the benefit of using composite materials is the very long lifetime that they have. We have seen fiberglass boats, for instance, from the early 30s, still out there in the ocean sailing. So the lifetime expectancy of composites is immense. So be able to design structures where you can disassemble them easily and use the elements in other structures could also be a way to go. So you can when you're outside of your construction, you can actually just take the elements down more or less like Lego, and they use those elements in other structures. So that's a good point, but this is also obviously a point that is up to the designers and engineers to make.
That's it, really. Unless anyone else has got any questions, you need to throw them at us now.
As mentioned, we have a background papers for this presentation. If you are interested, please let me know. If you have any further questions or topics you want to discuss with me, my contact information will be sent out to you. Please reach out to me, and we can gladly present some numbers and information on all those slides and the claims that we make here.
Cool.
Thank you all for listening. Have a great day.